everyone. I'm really pleased to introduce Dr. Percival Matthews, who's here with us from the University of Wisconsin. So Percival is an associate professor of educational psychology and also associate dean of academic programs and special advisor to the provost and chancellor of access and community. And I first met Percival at the first meeting of the Mathematical Learning and Cognition Society at Oxford, and I'm very pleased to host him here at Penn. He did his undergrad degree at Harvard and then went on to pursue a PhD in political science at the University of Chicago. And he left that field with a master's degree to pursue his true passion in educational psychology at Vanderbilt, where he earned his PhD working with Bethany Riddle Johnson. And he went straight from there to his faculty position at Madison. He's been continuously funded by NSF, in addition to being awarded a James McDonnell Foundation Scholar Award in 2018. And Percival studies mathematical cognition, and he has championed the idea that we rely on a ratio processing system for intuitively reasoning about proportions and ratios that may actually be foundational for fraction learning. And I think he'll focus on this basic science work today. But he's also worked on adjacent questions with educational and practical applications. For example, he has written about ideas of how to foster diversity in the field of mathematical cognition. He developed new age-appropriate assays for studying fraction knowledge in children. And he worked on a fun intervention that tackles the well-known whole number bias, where people think large denominators are bigger numbers compared to small denominators. That intervention actually was found to be useful for tackling reasoning about COVID risk. So without any further ado, please join me in welcoming Percival Matthews.
Hello, everybody. Can the people, you'll tell me if the people on screen can't hear me, right? All right, so zero order issues. As of like 2 weeks ago, now I'm like a real live full professor. Like they used to let me associate with them, and now I get to what?
Gotta update your CV again.
Yeah. I want to say thank you. Usually you say thank you after the talk, but I've been in so much admin work lately that I haven't gotten the chance to just sort of play in the ideas the way that I like to as much lately, and so I really appreciate it. Even if you hate the talk, thank you. This question, are fractions natural numbers too? We talk about these counting numbers as the natural numbers. There's a little clicker, right? I think it got put back in here. And so I asked these questions about ratios, and I want for you to go ahead and ask questions when you have them. If there's something where I say, yeah, I think we need to move on a little bit, we can do it. But what I want to do is play around a little bit. The talk, there are plenty of places that are natural enough places to stop. So if we start, a lot of times, how does this work?
You're using this computer?
Yes. The desktop. I can use I can use keyboard. That's fine. Keyboard's good.
The keyboard does work.
I still use paper too. Everything's fine. Paper.
You can just use it up and
Yeah,
down if you're comfortable with that.
Quite comfortable. So I can skip part of my shtick because you guys know Dr. Liz Brandon, but a lot of times when I start, I do ask people like a simple question just to sort of, and I say, hey, I'm gonna flash a word up here, and I ask them not to read it. And it goes like this. And then I ask them, did you read it? And they're like, yeah, of course we did. And I'm like, why'd you do it? I just met you, asked you to do one thing. So it's really interesting when you start thinking about, human beings existed for all this time. And most of them couldn't read for most of this time. And now you read so well that it's just ballistic. You can't stop yourself from doing it. So how is it that this human brain, even if there's strong arguments that it evolved for language, didn't necessarily evolve for the orthography specific to the English language? Like, what is it that we come with that allows us to do that? And I do ask, some of my work does ask this question about, I would say, numbers and about math more generally. The one thing that I would say that is a little bit of a difference in how I look at it is there's a question of whether we use these architectures for our mathematical thinking versus do they exist for us to use them. And I think those are two very different questions, right? It's almost like if you see somebody hammering in a nail with a brick of cheese and there's a perfectly good hammer sitting next to them, like you can give them a shinier, harder hammer, but if they aren't using it, where sometimes even a bad hammer if you learn to use it. So there's like different sides of what you do to get somebody to use it versus what sorts of tools are there. But when we ask how is it that these evolutionarily ancient brains came to be adept with number processing, I don't speak fast because I'm nervous. I do it because that's how I speak. And I am capable of slowing down for 3 or 4 minutes at a time. So if I get to going too fast, just ask me to slow down. I'll slow down. I'll speed back up over the next 3 or 4 minutes. And then we can do that again. And so you guys have heard about the ANS before. Now, but could it be ratio, right? So you've got this old Chronicle thing where it says God gave man the natural numbers, all else is the work of man. And it's really weird where like kids have so many problems with fractions. And if you look at, oh, we got people on camera. And if you look at what people do, lots of times we teach people 1, 2, 3, 4, and then you count 3 of those. So I count it to get to a number that you can't count to. And we wonder why people have so many problems. So is it that we're starting with these counting numbers, and is there something else is a big question. And so are there some other foundations that we might have for numbers that are at least as important or as important as our whole numbers and our ANS sorts of things? So when you start looking at a lot of our theories of magnitude perception, they begin with these extensive quantities. It's how much stuff is in a system. Mass, it increases with how much stuff there is, how many different numbers there are. So whether we're talking about this in terms of the actual number of things there, in terms of the surface, and in terms of the area, there's all kinds of other ways we can think about it too. So we do have these intensive quantities. Think density, right? And so when we think about ratios, here are these things that are defined relationally, which would give us another way to think about numbers and all sorts of other things. So when the microphone's here. When I started thinking about this, it just sort of happened into it. We were looking at the ways that we think about a task, we are comparing these numerosities. And if you think of it as sort of a subtraction over a log transformed thing, just go back to your algebra 2. That's the same thing as, the logarithm of the ratio. So it's this question, if your difficulty is indexed by this difference, but this difference is also directly goes with the sort of ratio between them. Is there a way where what we're actually perceiving is the ratio instead? Is there a way in which you can rethink of that difference as perceiving what the ratio is? And anytime you read something, you do something and you think, hey, I've got this good idea, and you look around long enough, oh yeah, Vern von Veit did that in 1974. You just keep looking. There, you might have to go to microfilm or something like that. But so I started asking this question: what if we did go ahead and foreground ratio? What would happen here? What if our basic perceptual apparatus really is more naturally in tune to ratio than to discrete whole numbers? And then what if we sort of leverage this ratio processing ability to think about symbolic numbers more generally? So when you think about fractions and ratios, but even whole numbers, there was a question that came up at dinner yesterday, and there were a couple different ways to think about it. One is, what is a number? One is, how is number represented? To answer that second question, you go back to what is a number? And there are ways that you can think about numerosities, dot arrays as numerical analogs. There's certain cases where you go to and they're like, well, do you have number if you can't use it in the ways that humans use it? And there's a lot of different ways to think about this. And so what if this ratio is another way to even get to our whole numbers? So there's a bigger question. What if ratio is a way that we can leverage our generalized sort of perceptual apparatus? So these different ways that we perceive magnitudes, whether you're listening to that fan out there, right? Whether you're looking at differences in light intensities, whether you're perceiving differences in temporal magnitudes, what if there are ways that our general psychophysical apparatus easily maps to number and that we might be able to leverage this. In fact, this is how I started working this. When I started doing this work, Bruce McCandless was showing something from Piazza, and I was like, well, what if your ANS doesn't work right? Do you have something else? And so I was trying to figure out if I could get a hold of a bunch of dyscalculic children and what else would they have intact. But anyway, this sort of grows out of questions like that. So you got this big problem though if you want to use continuous magnitudes. So if you want to use a line, right? What does it map to? Is this 1 foot, 1/3 of a yard, 7,200, you know, like 5,200 of a mile, 1,760. So individual magnitudes like this don't necessarily map to specific numbers. And so when you start thinking about something like number lines, I started thinking about what you could do here. So a lot of times with the number line estimation literature, they're thinking about something that was specifically about educational outcomes. There was Opfer and Siegler who started talking about how it relates to the way that you perceive numerical magnitudes, but there was something that once Hilary Barth got a hold of it, that pulled it back to psychophysics of perception that I thought was really interesting. And so there's one thing about a number line that is really sort of incontrovertible. If you think about what you have to do a number line, the distance from the 0 to that hash mark has to be in relation from the distance to the 0 to the 100, the same as it is a 74 to 100. So in order to complete a number line estimation task, it is a cross-format racial matching task. It just is. What happened to it? So if you think about number lines, you can put them on a paper. You can do them on a paper this big. You can do them on a paper this big. They can be arbitrarily large for you to be able to do them properly. And I'm not necessarily saying how you make that map, but at the end of the day, you have to be able to make that map for it to work. And so I started to think through what would be involved in making that map. And so again, here you have these two extensive magnitudes that can map to, they just don't have a specific map to number, but when you put them together, they map to a very specific ratio or its inverse. So it's inherently relational. This is a stark contrast to this idea of sort of grounding numbers 1 to 1 in numerosities. There's more to say about that a little bit later. I don't want to offend anybody's sensibilities. I'm coming back. I'm not poo-pooing numerosities. The only thing I have against numerosities is that they're too complicated. It's like anytime you have something where I can look at the individual numbers, an individual number of them, or I can look at the area, or I can look at the convex hull, or I can look at the density. That's why I really was excited when Emily Scoot-Lauer come to work with me, because I was like, oh, she can do the numerosity stuff and we can work with it because she thinks about that better than I do. So there was this big question, could it be ratios all the way down? And what I want to do is take you through a thought process of how we would look at that. So first, like, are ratios necessarily advanced? When you talk about certain mathematical concepts, certain numerical concepts, people think, oh, this is advanced. You can't teach a kid until they're a particular age. But you know, McCrink, when Colleen McCrink had this, she asked me to stop showing in like 2012 because she hadn't had tenure yet. And so she wanted me to do something that was more recent, but this is my favorite one. She's all good now. You know, when she had these 6-month-olds habituate to these pictures of Pac-Man and power pellets, and they habituated to the ratios between these things. And I thought that was really interesting. And then you had all this stuff with Spinello and Bryan in the ed-like space where they could match across different ratios. And then there was this really interesting thing with Duffy, Huttenlocher, and Levine. But what they had in this task, okay, I'm going to use the mouse, right? Because the people online can see the mouse. Is they have these little wooden dowels, this was this great thing, and they had them in a glass container. And the task was to pick which of these two had the same size wooden dowel as this. All right, class participation. Which of these has the same wooden dowel as this, the left or the right? Yeah, you can probably read the target foil thing too, yes. So oddly enough, a lot of the kids, when you did this one, they picked the foil. So here's this thing where all they had to do was match the heights of the dowels, but they often picked the thing that was actually a relational or proportional match. And then, of course, we go back to our number lines. So we've got all this work that shows that these children with no formal fractions education minimally have this sort of sensitivity to some sort of fractional or ratio analogs. And then, it's not just the kids, it's the lions, tigers, and bears, right? So, interesting enough, there's this old stuff that Nieder used to do. There was Jacob Nieder's Valentin Nieder, Jacob Valentin and Nieder. They had a really cool Tix article in 2012, and they were using these rhesus macaques. And what they were doing is a match the sample task where um, the monkey would see a pair of lines, and if you look at it, this is in a 1:4 ratio, this is in a 1:4 ratio, but it's jittered. This is in the 1:4 ratio, but they're different lengths. And they were supposed to release it in the gap of juice when they saw one that was a match. And so this red line is what their responses were when the first thing they saw was a 2:4 ratio. And what you see is when it matched, they were judging it, saying the sample close to 100% of the time, and then it falls off as it went further off. Now, what I didn't put up here is they were as good at that as the college students. So, does a monkey have the language and the fractions knowledge? I think most of these kids are going to beat them on the SAT, but they weren't beating them on this match the sample task, which says something about this perceptual sensitivity to these analog magnitudes. And then all kinds of people, I didn't put Liz's stuff up here, with the monkeys that have, with apes, that have this sensitivity to ratio. So, why would ratio be so important? Can you tell me what the difference is between these two bottles? Anyone got an idea? I used to looking at the neck. One has a bigger neck, right? I got this from Dora Abramson, actually. It's a camera trick. So one is closer to you. So, but when you're first looking at it, all you saw was the difference in the neck because the aspect ratio is conserved. So I get closer to your retina and this thing is bigger, 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 but what's conserved is the aspect ratio. I get further from it. Now, if I cut it in half, then the aspect ratio changes and you notice it. Like, we're really sensitive to these things, and you can see how it'd be useful for all kinds of things. Everything from recognizing an object, its shape, to wayfinding, to all sorts of things like this. So it might just be something that is a feature of the world that had an evolutionary purpose, has an evolutionary purpose, so you would see where this comes from, and we can use it to mathematics. So again, what is it that this phylogenetically ancient brain has that we can apply to these new sort of cultural inventions? But there's this question, is this abstract? Is this just scaling? Is this just scaling something up, like, or is there something more abstract in it? And so I wanted to ask this question. And here's this outline for proof of concept that it might be more abstract. I'll show you a series of things. One is just I started off with looking at the way that adults could accurately map these sorts of non-symbolic ratios to number symbols. I'll show you something that goes across different formats to look at the abstraction when you do that. I'm actually going to skip this one. I could talk about a little bit, but we only have so much time. I'll show you some work about the correlation between these abilities and higher order processing, reasoning, and then I'll show you a little bit of comparative development stuff. I think that if we get through the first two with plenty of questions, it'll still be easy to stop, but we can stop at any of these points, all right? So, how did this start? I am at Notre Dame. I think I might have cut part of the CV off. I'm sorry. I was at Notre Dame with Nicole McNeil. And I was writing an RSA, and it had to do with number line estimation and the great race. You're playing these little games, and she looks at it and she gives me this feedback, and she's talking about what she doesn't like about it. And what you usually do is you just sort of dig in, and you're like, no, this is why. And I looked at it and it was like, yeah, she's right. That's not that cool. And as I was looking at it, I was like, oh, but this part of it is. And so that was when I started looking at the non-symbolic ratio part of the number line estimation. And I wanted to know what people could do in general. So what I first did is I just printed off a bunch of things. I was stopping people walking down the hall, Hager Hall, and South Bend. And I was saying, hey, if I ask you to look at these dots, and don't think about the size of the dots, just the number of dots on the top versus the number of dots on the bottom. Like, what would you give me for a number, for a ratio, fraction, however you want to do it? And people all said, hey, I don't think I was very good at this. But they were all pretty good. So then I would flash it for 1500 milliseconds. And they were all pretty good. So then I would flash it for like 500 milliseconds. And they were all pretty good. So when I looked at this and I just plotted what their median estimates were versus the actual stimulus ratio, like this thing had a slope near 1. It was linear as all get out. it was just something they were able to do really well. So here comes the next question where people are like, well, what if they're just calculating? What if what they're doing is they're just looking at the number of dots on top, they sort of have an estimate of that, and then there's a number of dots on the bottom, and that's how they're doing it. Now, if I ask people what they said that what they were doing, they didn't think that was what they were doing, but people often don't know what they're doing, right? Um, and I never thought that that was really what was going on, because we've known for 100 years that once you get past 9, right, you go back to Taves, you go back to Kaufman, Lloyd, and Rees, these are logarithmically transformed things. And the log of x over the log of y is not the same as x over y, but people are getting really good estimates here. But we had to find a way to deal with it. So it's like, well, what if you just use these circles? So here's this task that people aren't used to. And I'm like, think about the area of this circle over the area of this circle. What do you get there? And people were like, hey, I really was bad at this, but they were actually better at it. And if you think about this, most of them wouldn't necessarily really, I didn't give them a ruler. And if you give them a ruler, a lot of them would do the ratio of the diameter to the diameter. But area goes as diameter squared, so that wouldn't have worked. So people did this. Again, you could flash for 1500 milliseconds, you could flash for 500 milliseconds. It's not easy to partition this up. If you partition it, the slices aren't the same, right? You're just doing it by a sort of feel. It's continuous. There's no counting or partitioning. It's all feeling.
Sorry, Percival,
Go
what
ahead.
were their answers here, or what kind of report are they giving?
So I've done it a couple different ways. I've told them to give it in a fractional format. I've allowed them to openly give it. It was just a string response on the computer. So some of them use decimals. Most of them use fractions. What you'll get is they'll use common fractions or common decimals. So what you get is things that are slightly quantized. Does that make sense? Yeah. And to go back here, sometimes they were seeing as few as I don't think any of the parts were ever less than 17, and sometimes they went up to like 250 or something like that. So what I wanted to know from this is how abstract is this again? So what we have right here was something that is within a given format. And what I wanted to know is, could people accurately compare these analog values across different non-symbolic formats? So what we were going to do is to actually ask them to compare the ratios. I've got people on the screen. The ratios that are made from the circles to the ratios that are made from the dots. And I wanted to know, could they do it fast and could they do it accurately? So before I show you what they did, I'll say what the data would look like in an ideal world. In an ideal world, what you guys are going to see is I'm going to put the data up, and it will be a distance down here is going to be the dots minus the dot fractions versus the circle fractions. So on the right, dots are larger. On the left, circles are larger. All right, and then just the y-axis is the proportion of time that you judge the dots larger. So in an ideal, completely, if you were perfect, there'd be a step function here. But because it's perceptual, you're going to have something in there, you get this little oji. Does that make sense? And then sometimes they saw the dots on the right, and sometimes they saw the circles on the right. So if they can do this well, it would go towards perfection, towards the end, and we want it to be really fast. So what we got with these data was this. So if the first thing that caught me off guard when we got it is it was just really pretty. And if you looked at like individuals, most of them, it was just really pretty. And then it was fast. So they're doing this in 1100 milliseconds. Now, if you look at the old sort of Alberta numerosity discrimination tasks, quite frequently people aren't doing that much faster than this. And this is something that has 2 different formats. So it was really fast. It was too fast for you to be converted to symbolic numbers first. Again, if you ask people to compare 3/4 versus 5/6, they take longer to do that than they do to do this. So you aren't converting both of those to symbolic numbers and then comparing them. The other thing that caught me did it catch me way off guard? So the fact that this point of subjective equality here, where 1/2 equals 1/2, and it was like 50-50 for people, the fact that that's where it was caught me off guard. And I'm going to go a little bit into the weeds with you guys, so I think you might find this interesting. So I don't show most people this. It's in an old paper from 2015, but it's a long paper, and nobody reads past page 10 of a long paper. So when we did this like this, where it's symbolic fractions versus these ratios. It was fast again, but what you got when I was trying to plot out sort of distance effects was this. So you see this serious discontinuity here. And I don't remember why I first saw that, because lots of times what you have is like you just put the absolute value there. So it would have looked like it normally does. And I can't remember why I plotted it. I actually can't. But there was this really interesting thing where I'm like, this error rate, why is this jumping up like this? But when you plot it like as this O drive, what you see is something that's actually really well behaved. It's really smooth. There's just this bias there. There's this bias where they're seeing these circle fractions. When you map it to number, they're systematically overestimating the size of them, right? And so it's really interesting because I don't always know how to talk about error anymore. It's like if you correct for the bias, this thing looks the way that you expect it for it to look. And so the smoothness is actually what's really important. Now, and a question that you would have if you're paying attention might be, well, where does this break down? Clearly, if you see something that is 1/100th, you're not going to think that it's actually 1/10th. And I would say that's a really good question. I haven't really analyzed it very well yet to answer to that. But so I have this graduate student now. She's in her first year, but when she was an undergraduate, she was one of those undergraduates who's like really quiet. If it were a participation score just based on how much you spoke, it just wouldn't be there. And then they write the paper, and you're like, oh my God, can you please stay around forever? And one of the things that she's really interested in, she's an artist. She does lots of calligraphy things, plays like 4 different instruments. And she was like, well, what if we do this? Percival, we've done these in a lot of different visual modalities. We've done it with these blobs, these lines, you've done it with dots, you've done it with circles and things. Have you tried doing it with sounds? And I was like, Carolyn, like, I think that's a really interesting question, but if we're asking people to memorize a ratio with sounds, like I can't present those sounds in parallel like that. We're gonna have to do it where they're hearing something, and she really wanted to do it. And I was like, okay, go ahead. And so she has these things where like if you look at this, they're just there's actually a temporal ratio with sounds in different pitches. So the first one will be like boop, boop, and the next one, boop, boop. And so and she's comparing those sorts of ratios. And then she sometimes did it where she was comparing the temporal ratio instantiated by sound to the one that is done with lines. And then sometimes instead of showing both the lines at once, she would show a green one and then disappear and show a blue one to sort of mimic what's going on with the serial presentation. And so the question was, could people discriminate these ratios across these different modalities well? And then what were the differences in the bias patterns? I'm capable of waiting just a little bit. It's easier than slowing down. Okay. So if you look at there's a zero order thing, which is, well, what happens within within stimulus. So if you look at the lines compared to the lines, again, people are really good. You get this steep O drive in the middle. When they do the temporal like sounds, the sound ratios, again, they can still do it. It's just a much flatter sort of discrimination. I was surprised that they could do it as well as they could, though. I thought it was going to blow up because memory decay and things like that. So what happens when you do it across different formats? So you'll see here in the center is the sounds versus sounds. And one of the things that is consistently striking about this is when we do it across modalities, and this also happens when you do it across different visual formats, what you'll find is the comparison across format is usually not that much worse than the within formats for whatever the noisiest signal is. So they were able to do these things, but you do get these sorts of biases. I don't know where they come from or how to map them quite yet. It's a big question. Anybody who wants to help answer that question, I got all kinds of stimuli I can throw you away. I think the most interesting paper I've seen of this was there's this old paper from 2009 with Veronique Izard and Stan Dehane, And that's a paper where by the time you get to page 27, so most people have stopped reading it. They have this idea about what happens when you're doing the estimation step. And then one of the big differences between that study and this study is, in that study, they will show somebody, they're using numerosities. They will show somebody dots, and then they will ask what number that is, which is different from an alternative forced choice task that is much faster. But when they're making that map, they have an interesting sort of thought about what kinds of affine transformation a person might be making. And I don't know how that necessarily applies here. We've just started collecting a lot more data on what happens when you do something like compare performance on a task like this to a task where you show the non-symbolic ratio and ask them to estimate. Like, do you get similar biases? What are the differences? Is the bias that you get for the alternative forced choice task consistent with the one that you get for the estimation task where you generate the number? So this is all getting at the fact that people are pretty good at mapping these non-symbolic ratios between, and one of the things that I think is really cool about ratios, there's lots of stuff that's cool about ratios. I mean, we're psychologists, right? So as psychologists, I mean, look at all your tests, right? You got an F test, you got a mean square within, a mean square between. Like, we do lots of things for ratios all the way down, but it's like apples to apples. Can you compare apples to oranges? You can compare a number of apples to a number of oranges. You can compare a ratio of apples to oranges. It's really interesting to think about what this allows you to do. There's this old Balchi and Galliso where they're starting to talk about comparing across different modalities. And the easiest way to think of that making sense is when you do something that is ratio, because when you go to ratio, it can be dimensionless. All right. How much time do I have? Okay. So let me show you one quick, I'm going to skip this one. Let's go. Can we just skip to the developmental part? Okay. So, with little kids, it was really difficult. This is Blythe a few years ago. It was difficult to think about whether or not the little kids would have the same sort of sensitivity. And here I write RPS because lots of times we write about the racial processing system. I actually hate the term. You saw when I was talking about, I was thinking about an analog magnitude system that deployed a slightly different way would get you there. But I had co-authors and they were like, yeah, but you have this approximate number system. Well, it doesn't racial processing system. I was like, I mean, it sounds good for marketing. So I went with it. And I tried to stop using it, but then people would ask me to use it again. So I'm like, fine. So that question, is it separate systems? Is that was never what my claim was here. But we had these kids, and I was trying to figure out what we could do with little bitty kids, because when you do something like this, you can say to an adult, look, I want you to think about the ratio of the white to the black, not the overall size of the white and the overall size of the black, but the ratio of the white to the black, and then compare it to this, and that gets to be really wordy, really fast. So what we did for little kids was a match to sample task. And I have this up on my computer, but let me see if I can do this here. So I used to go to these daycares. And what I would do first is just ask the kids, hey, which of these is the same as this? Hey, which is the same, top or bottom? Bottom, good. Which is the same, top or bottom? You said top? No, look. You can see, and so we didn't really try to explain it. We just trained them up the criteria to see if they could do it. And after we got them used to it, then I think I need to refresh this for it to do what I need for you to see, because I need for you to see that this is not always easy. All right. So I'm going to go to a harder one. What I actually gave them mixes things up after they go through the training, but I just want you guys to be able to see this. So don't be afraid. Yell out. Which one's the same, top or bottom? Y'all. You can't be afraid. You gotta yell it out. Top or bottom? Okay, I'm hearing more bottom than top. Okay, which is the same, top or bottom? Top or bottom? Okay, so I'm doing this at this daycare. Sometimes the 4-year-olds are beating me and I do not like it. But, so, but, what happened? I never stopped this. I am on Zoom. I'm sorry, what's that? You said go to,
Go to the top.
Top.
PPT again. Just open PPT. And
just open the PPT again. There it goes.
Oh.
Sorry. My slight difference between. Okay, so when we did this with little kids, we had several different ratio bins. The 3-to-1 is the easiest, as you can see. The closer it gets to them being the same, the more difficult. What you're expecting is something like this. So here we have, I'm sorry, there are arrow bars here. Pre-K kids are animals. Like the difference between like a 3-year-old and a 4-year-old is a heck of a thing. So you're expecting for it to go down near 50% as these ratios get close to 1 and to go up towards perfect as you get older. So the first thing with circles for you to realize, 5th graders are often beating the adults. If it's a perceptual task, it makes a certain amount of sense because your eyes are really good when you're 11, right? I'm at a point where I need the selfie stick to read my writing. Same with the line ratios. Now, you'll see that when it goes to the pre-K and the kindergartner kids, you get the same sort of pattern, but they're not quite as accurate, but they still get the 80% accuracy. Here's a kid that does not know what a fraction is. Now, it was the university preschool. So if you do the PPVT with it, it'll take you a week, but most of them don't do fractions, right? But it was also clear to me that some of the students didn't understand the directions very well. So I just did, if you take a median split and you take the top half, it looks more like this. So again, you got these top half of kindergartners and pre-K students, and they're doing really well because here's this thing that really is this perceptual sensitivity. Do they understand fractions? No. Do they have a perceptual sensitivity, something that is an analog that maps to that? Yes. And so one question is, once you know that they have that ability, can you leverage that perception? Which I think is a substantially different question, but it's one that we want to use background work to get at. So, we had Yunji Park, whose picture is not up here. Yunji's looking for a job. She's working with Vinod Menon right now. For her thesis, one of the things that we were looking at is when we say, are these two different systems? And so this was a clunky way to get at that question, but it was, hey, let's do this across a couple different ages, but let's look at how students do on something like when they discriminate between 2 lines. And if this is really the source of them to be able to do their racial discrimination, then you might think of this as a limiting factor as far as how they'll do on the racial discrimination. So I was expecting for how well they did on these individual extensive magnitude things to predict how they did on the ratio better than how ratios predicted how they did on other ratios. And so for Yoonji's dissertation, one of the experiments have 42 preschoolers, 29 5th graders, 31 2nd graders, and then undergraduates. And we had them do different tasks like, like what you can see here. So we use circles, lines, dots, inspired by Durkheim Odic. We were using blobs. Quick story about blobs. This is why you always call people and ask them how they got their simulate. I'm like, man, how did this dude make this blobs? I don't know. I found an undergrad who's now studying. He actually finally graduated. He was doing climate science at Harvard after he left us. He was a computer scientist. He's like, well, I don't know how you do it, but what I could do is I could draw this ellipse and I can introduce these perturbations and you can, and he made this thing that was really cool. So then I finally saw Melissa Livertis. I was like, how'd you guys do that? She's like, we drew them. I was like, but, if you look at what happened when they do these tasks, for the ratio comparisons, we consistently saw that if you look at the accuracy, the adults are up higher than the younger kids. But what you'll see time and time again is that people are better on the line format, worse in the dot format, and somewhere close to equivalent on the circle blob format, which I was wondering, hey, is that a topology thing? And then today I saw that there's somebody in this room who was asking questions about the topology thing. Name rhymes with Manon. So even the little kids were pretty good at this. And then when we looked at what these relations went, and again, this is a clunky way of looking at it. Um, I was expecting for the within format sort of extensive to be related to the ratio more than for the ratios to be related to all the other ratios. And that wasn't what we found. The ratio was more related to the other ratio. You can think of a number of reasons why this might be when I say it's clunky. Some of our next steps is to do replication where we do a lot more trials and we start using things like drift diffusion models to think about what's going on. Because there are a few things that I don't talk about in these studies. Like, for instance, if you compare a circle ratio with a number, circles to 3/4. If the circle is on the left, people go faster than if the number is on the left. And I found that consistently when I use the non-symbolic. The non-symbolic is on the left because people tend to read left to right. There's something about that non-symbolic being on the left that makes them go faster. And the question is, I mean, I don't have a theory for why they should be able to extract information from that any faster. But is it that when they see a number, think they're supposed to stop and think, but when they see the non-symbolic, they don't? And with a drift diffusion, you might see a difference in uh, the boundary separation, right? So go ahead.
Okay. Hebrew, thanks a lot.
So I have never thought, I don't know Hebrew. I have seen some of the things that were done with narc effect and thinking through Hebrew and a couple different numbers in Hebrew. I'm going to have to think about that with ratios. That is interesting.
They should be better.
So get a
If it's about
Get-
getting the thing first.
so I think I could get a population of Hebrew readers and I could look at that. I think that's one way to do it. I also think that with the drift diffusion, if you see some differences in sort of boundary decision, how confident people need to be to make that decision versus no real differences in the drift rate, that'll show us some things too. But thank you for that. Sorry. All right. So there's all kinds of questions like, what about kids like this? This is Cadence. Cadence is 7 now, but there's only so much that I've gone down to age 3, but I haven't used these sort of infant looking paradigms and any kind of infant paradigm. So it's interesting to think about what will happen with the kids. When you start thinking about this as a potential neurocognitive startup tool, it'd be like, for what? All like when you start thinking about nomothetically, where all could this go? But I am going to take you back to the beginning now. Let's go back. I talked about how these things map to number symbols in adults pretty well, like really well. So it's the fact that somebody can. Then there's a question of how do you get them to be able to do it? It's relatively abstract in that you can do it across different types of visual formats, but you can even do it across modalities. I was actually surprised if you could do it as well as you could with some of these things that are presented in series and different modalities. I didn't show you the thing where it's correlated with higher order reasoning abilities. I never expected for that to work. Here's an honest story. Somebody's like, yeah, we'll do this and it'll predict algebra knowledge. I was like, why would it predict algebra knowledge? It's like, well, the ANS stuff did. I'm like, that's not a theory, man. It's like, I was like, look, I'll give you your theory. If we were going to do it, this is why I was going to do it. I was like, but it's not going to work. And Ed was like, we'll give it a bet. And it worked. I was like, that I didn't trust it, but it was data and you did it the way you're supposed to do it. And you're an assistant professor trying to get tenure. So I published it. And then Yunji Park went through and we replicated it and it happened again, but almost all the action was with the line ratios for what that correlation was. But if we come back to how is it that our evolutionarily ancient brains come to be so adept at processing number, and we think about numbers, is this a number? Is pi a number? 3.141592654 goes on, has lunch with God, right? Or you can take that circle, you can unwrap it, and you can put the circumference here, and you can put the other thing there, and it's pi. So maybe this is another touch point we have for number. And so what happens if we foreground something like ratio? And there's a sense in which we do it all the time. So these number line estimation is actually a really big deal in the ed psych space. And what you do with these number line estimations is you always already do something like this, which requires for you to have that ratio there. Like if you think about what a number line estimation task is, there's so many times we teach kids numbers, 1, 2, 3, 4, 5, and we teach them, we give them these like multiple redundant cues to what that number is, right? It's a beat gesture. You're doing it in time, you're not doing like a Sesame Street, 1, 2, 3, 4, 5. It's not syncopated, right? Like we give them all these things that lead up to it. And so if you look at numbers, it's like 2, 3, they start off, and a lot of times they don't even know what it means, but they have a nominal thing, right? And then you can get an ordinal one, but when do they have a really measurement level number, a racial level understanding of what a number is? A number line estimation task is one of the few tasks I can think of that exists out there that routinely asks this of little kids. And so just thinking about what happens if we foreground ratio and thinking about number, I mean, on some level, this maps a number to every other number in the way that a dictionary lexicon maps a word to every other word. Can I give a quick little thing for word learning for the people who do word learning? Like I recently started wondering if like fractions are like red, right? So you have these things and these things have shapes, but then you have things with red shapes, but you're trying to get people to focus on the red. So if people can see ratio and they're always now you're trying to figure out how to get them to focus on the fraction. So the question is, if we think about what we know about how to get people to learn certain classes of abstract words, will that help us think better about how to get to learn certain abstract classes of numbers? If you want to help me with that, I'd be grateful. Thank you. Okay. So as far as I'm finishing up, yes, I'm not gonna do this. I'm going to say that with the basic science, if we move toward this sort of unified theory of numerical cognition and magnitude perception, there's something in the ratios that allow us to potentially do that. I think that what Barth and Palladino did with some of this number line estimation was really powerful, and there's something that can allow you to do that. I think that when we think about education, we've tried a lot of different ways to get people to think about fractions. And one question is, if we leverage something like a signal that you get from the world and we explicitly leverage that to get you to understand the sizes of these things and how they relate to each other, will that make it so that you have a more powerful understanding of a fraction? And even certain whole numbers is an interesting thing. And then we'll end with the thanks. We'll thank all the people who help. We'll thank the funding organizations, and hope they're around next year. Thank you, guys. Go ahead.
In terms of thinking about stuff like word learning, you asked like, do we have to about 5, 7? Some people think about certain things like modals, like it could happen, certain uses of it as being probabilistic, or just like possible, likely, you know. And I guess is that something you want to entertain as related to, I don't know, representation of ratio that maps onto a word, or are you thinking about something different? Like if I ask you if I say something is likely to happen, how likely do you think that is? If I think something could happen, how likely do you think that is, right? We can get people we'll get like a distribution around certain areas, right? Is that kind of what you're thinking, or no?
So it's not what I was thinking. I paused because I'm wondering if it's something I should be thinking and wrote a quick note. What I mean is, if you want to teach someone what a square is, you point to a square, and there are enough different biases that children have that you can sort of do that. If you want to teach somebody what green is, it's a little bit more difficult, although that's probably qualitatively different, I think, from teaching somebody what, I don't know, enemy. Is right.
So your question is more about the word learning context that could get you to think about those things.
Yes.
Than the words.
To
they
get
might
you to
influence.
focus on, I think it's pretty clear that there is a signal there to be attended, what to which one could attend, and the question is how to point the attention that way if you're trying to train up selective attention, and if there are ways to train that up that could be informed by what we know about how people learn words.
No, Jorge Morales and work with Chaz did some stuff on observing parts of things and sort of imagining the wholes. That seems like, these are cases where, you know, like if you see like a portion of a butterfly, you know, it brings to mind that it's not the whole thing and sort of make it more accessible. And they do some perceptual tasks. So I don't know, that seems maybe in the direction you're thinking. I don't know if you think that's like a different literature, I guess, but maybe that's helpful.
Thank you. And that was simultaneous. Yeah.
I think that, how do you think about the relationship between this ability for ratio processing and, you know, the approximate number system? You can imagine that they're the same thing, like two manifestations of the same thing, or one of these is more foundational and the other is built on top of it, or they're completely independent. You could be really good at ratio processing and really bad at processing approximate number and magnitudes.
Yeah, I think that's a really good question. I think that somebody who's really good at thinking about how to parse through the racial processing right now, Michelle Hurst, is doing a lot of really cool things as far as like how much of it is componential, but that versus the ratio versus when you're forced to push part versus when you're forced to go part whole. I think that question is complicated by a couple of things. I think the only thing that I can say definitively, I can definitively say that I think that the ANS is not what is allowing you to compare line ratios or temporal ratios by sound. There's no argument that it is, I don't think, right? So it clearly isn't all ANS. So the question is the ANS just one special case of something that applies to our sort of psychophysical apparatus more generally? I think is a really good question. I think, but even when you look within the ANS, again, somebody whose name might ram Manon has this one study from last year where there are these dot arrays, and so you can have red dots, you can have blue dots, and you can collect them with little barbells. And one of the conclusions from that is when people are looking at this proportional judgment, you're asked, hey, which one are you more likely to get a red dot? When people are using this proportional judgment, it looks like they're using a part whole. And I think that you really can see that from that paradigm. The question, and this is where I think a lot of Michelle's work is really interesting, is like, can minor changes to the stimulus or minor changes to what you give somebody as a task fundamentally shift the way they look at those things? So if you have two dots like this where you sort of can get a hold of gestalt, is there something there that makes it like a number line estimation where you use the stuff that you know, there's a bunch of people who did. I mean, Spence is a really popular one where the way you model it is you have this piece and then you have the transformation of the two parts and you do it that way. Whereas when you separate it, you're going to do something different. And I do have a hidden slide because there are always hidden slides. That I cannot find. Yes, I know where it is. It's right here. So, you know, we did this experiment where the old Stevens stuff, 1957, the old Stevens and Gural, Stevens and Galanter, they're all old psychophysical scaling things where you show an extensive quantity, but you ask somebody to give a number, but you're asking the number that's proportional to it. So that's one way of thinking, well, maybe what you're doing is you're guessing, you're saying what this is, but it's compared to a modulus somewhere. Or, so what I did is I took these tasks and it's the same dots. And you can ask how many dots there are, but you're asking them to give whole numbers, but the whole numbers are supposed to be proportional to other dots. You can use the same task. You can ask them to do it on a number line, basically. You can take the same thing, you can make it a numerator with another thing like this. And the long and short of it is, did I put this? The other slides are hidden. That's why you don't do the hidden slide quite like that, jerk. When you use the same thing, you get these vastly different patterns. You both get vastly different patterns in what your medians are for your estimates. So when you just ask them to give you a number, you get this massive underestimation, right? When you ask them to do it on the number line, you get this thing that sort of goes over and under, almost like a cyclical power model, where what you're doing is looking for something that's close to the center. And when you ask them to give you a fraction like this, I mean, well, that's even bounded because there a lot of times they're expecting a common fraction 0 to 1, and they can do them all relatively fast, and the error patterns are different. So I think there's even a question that with given a stimulus, how do you deploy the ANS? And I don't know enough about some of the time courses. There are a lot of ways that you could investigate that, but I think it's a really interesting question. Sorry for a long-winded answer.
Okay. But we're all gonna stick around a little bit more to talk to Percival.
Thanks, everybody.